more about generators than I do. And then operation in weak grids and island grids. What are the special challenges in this? And wind energy markets, maybe. So this is actually the Energy Research Center of Lausanne. This is one of the very first windmills in the world. A Savonius type windmill, which just runs on different CP values of like the of a rotor, front and back side of the rotor. This is also very early type wind turbine. Then, like these type of also drag type wind turbine rotors were used for water pumping throughout the world very often. And this is actually the concept. You've got a CD value which results in a force. And if you cover the counter-rotating, not counter-rotating, but the blade moving into the other direction, you can use this force to provide momentum on the shaft. So different kinds of Savonius type rotors are available, and the further development of wind turbines started with, like also historically started with the lift type blade. And you probably know how the lift type blade works. If not, I'll tell you quickly. The blade moves. Yeah, it moves into this direction here, and the wind comes usually from here or from there. And then you've got different angles which you like to adjust the blade according to the wind's movement. And now if you add up the vectors of the wind speed and the movement of the rotor blades, you get a resulting vector. And that is the vector. It has got a speed and an angle of attack towards the blade. And each blade has got one angle of attack which is optimal for the lift, like for the lifting force. If you decrease the angle, like going to this direction, you will cause turbulence at the end of the blade, because the air flow goes here around there and is not laminar here anymore, and it causes turbulence in this direction, and that is what we call stall effect. If the blade is like the angle is too flat or too large, there's an angle down here, and the air comes from here, then the lift force is very low, because the pressure above and below the blade are very similar, because the speed around the blade is approximately the same. So this is what we call pitch. Okay, stall is when you move the blade in that direction. The wind comes from here. If you move the blade in that direction, you get like turbulence behind the blade, that is stall. If you move the blade into this direction, you reduce the lift force, that is pitch. And then you can get curves like this here. So this is the like equivalent or linear to the lift force, and this is linear to the drag force. And you have got, in this diagram, you have got the angle of attack. So if you choose an angle of attack of, for example, some 18 degrees, 17 degrees here, for this type of blade, this diagram changes with the type of blade, so there are so many different types of blades. And for this specific type of blade, for example, if you have some 15 degree of angle, you have the maximum lift force. That would be optimal for optimum power production. Yeah? For example, in the range of some 3 to 10 meters per second of wind speed. If you go above 10 meters per second, this force, this lift force here, causing the torque on the shaft, might be too much for the generator to keep the generator at a certain stable mode. And that is why you reduce the force, like the lift force, either by turning the blade into the pitch direction. Yeah, that would be turning this blade into this pitch direction. Then you go in this diagram. You go down here, simply reducing the lift force, and the drag force is very low in this case. Another option would be turning the blade into that direction. That would be the stall direction, and then you go over here. The drag force gets incredibly high immediately, but the lift force is getting reduced. So this is like you've got active pitch and active stall wind turbines. You could also design a wind turbine with passive stall. Passive stall means that, as I already said, like if you add up the vectors, you've got a vector of this length, for example, for the wind speed. You've got a vector of, it moves somewhere there, of that length for the rotational speed. Now if you decrease, like the angle, let's say down here, yeah, the angle of attack would then be like this, yeah, if you add up the vectors. Now if you decrease the rotational speed, you can decrease this vector, and then you increase the angle. Yeah? And by increasing, like by decreasing the speed, increasing the angle, sorry, it's the other way around. So this, okay, you increase the angle, you get into a stall effect at the end. So if you, meaning that with a constant, assumed constant wind speed, by decreasing the rotational speed, you get less efficiency from the blades due to the stall effect, and that is what you could use to decrease the power output of a rotor at the end of the power curve, where you want to, like, on purpose, want to decrease the output, because if you further increase the output, it would destroy your wind turbine. And there are different types of rotors which use this effect. The Dayeux rotor, or the upwind or downwind, 3-bladed, 2-bladed, single-bladed rotor. Well, some have even got 4 or 5 blades. The Dayeux is a very, these days, is a very famous concept, but unfortunately, there are no turbines which really can compete in terms of cost-performance ratio, price-performance ratio, and in terms of power output with horizontal axis turbines. Well, this is what we probably know, like the power that is in the wind is 0.5 into the density of the air, into the surface of the rotor, into the velocity, it's 0.5 times the density of the air times the rotor surface times the velocity of the air into 3. Yeah? So that is the power that is in the wind, in the airflow. And then there is the thermodynamic maximum of what you could harvest from the wind, and that is the Bates factor. And this is approximately 0.59. So that is the theoretical maximum you could get out of the wind power. typical wind turbines have maximum efficiencies of 43%. It's not 59%. So usually, very, very large wind turbines, they even get up to 49 maybe. But you usually do not get above 50%. So these 59% are a theoretical maximum which can rarely be tapped. The small wind turbine sector has to cope with less efficiency. Smaller rotors usually end up at some 35%, 30%, 25%. If you go for Dahu rotors, as I just shown, this one up here, this type, Dahu rotor type, they usually have around 20% efficiency. And this is also the reason why they are, they usually cannot really compete with horizontal axis wind turbines. There are different types of rotors. And this lambda here, lambda design here, this is the tip speed ratio, TSR. If you have a tip speed ratio of 1, like tip speed ratio means the ratio between the tip of the blade divided by the airflow, the wind velocity. So if you have got a value of 1 here, like the tips move as fast as the air, like as the wind. So this, if you go at 1 or below 1, you have rather got a drag type profile. If you go above 1, like 2 or even higher, you have a lift type profile. The lower the number of blades, the higher the tip speed ratio. And this means that with the same wind velocity, these with lower number of blades have a higher rotational speed. So these turn slow, and these turn slowly, and these turn very fast. And well, okay, and then if you want to generate electricity, of course it makes much sense to have quite high rotational speeds, because this is how you can decrease the size of your generator. Otherwise you will need a gearbox, or a large gearbox, several steps, and therefore the turbines you see here, like with the 3 blades, they have 3 blades because, like in that case, the efficiency is quite good, the tip speed ratio is quite good, like rotational speed and nominal wind speed is quite good, quite high. And the second aspect is the optics and the noise emission. If you have very fast turning blades, like on the right, you get quite, like, and if you've got very, very long blades, large blades, you get quite close to the supersonic, how do you call it, like supersonic switching area, when you go from subsonic to supersonic. And that is, of course, that creates noise. And well, and therefore these 3 blades are a good compromise. All right, here we are again with, that is actually what I wanted to explain to you. Now, this is the triangle, actually, the vectors. And if you add up the vectors, you can have like wind speed smaller, the angle goes like this. If you say wind speed is larger, and you do not turn the blade, and you do not change the rotational speed, the angle gets larger here. And if you make it too large, like here, you get the turbulence at the end, and that is the stall effect. And the stall effect can be seen here in the power curve, where there's power versus wind speed. Here. Usually, the curve would go like this. like with a power 3 behavior. But from here onwards, you have the stall effect. So either it's a passive stall effect by just decreasing the rotational speed here. And this is the rotational speed. If you decrease the rotational speed, you get a steeper angle. You get the stall effect. Or by turning the blade into stall direction, from this into this, and you have got the same effect. And this is what you can see here. Oh yeah, why does it with stall turbines, why does it not stay constant? That is because the stall effect is immediate. It's not like the pitch effect where you can really smoothly and nicely control the power output. With the stall effect, it's like that. Either you have no stall effect, like here, you use the complete lifting power of your blade with the optimum angle, or you turn in the direction of the stall effect, and then the stall effect comes immediately. And then it decreases the power immediately by 30 to 50%, as soon as the stall effect occurs. And therefore you cannot control it that nicely here, but it's rather like, okay, if you go here, you rather decrease and then overstall a little bit, too much, to have a safety area up to here, because you cannot control it that easily. Yeah, this is approximately the same information once again. Okay, and now let's go into the wind regimes. The wind changes with height above ground. If you are here somewhere in 200, 300 meters above ground, you have geostrophic winds, quite laminar. Very nice winds to be harvested by wind turbines, but unfortunately you do not get to 200, 300 meters with your wind turbine, unless you invent a flying wind turbine. Yeah. If you go like below, let's say 150 meters, you get into an area which is like, from an aerodynamic point of view, a boundary layer. And in a boundary layer, you have zero wind speed directly at the surface, and the wind speed increases with height or with distance from the surface. And within this boundary layer, you of course you've got turbulence, and the turbulence gets more the lower you get, the closer you get to the surface. And this is always true for wind turbines. So therefore, like, the largest wind turbines we have in Germany right now are like 150 meters. They are here in this area. Quite nice wind speeds. But if you go into like the small wind sector, off-grid sites for telecom or village electrification, you're down here. Much less wind and very much turbulence. And this is what your control system has to take care of. The turbulence. And what is turbulence actually? What is turbulence? Turbulence has got two components. The first component of turbulence is the change of wind speed with time. And this can be very, very variable. It goes up and down and up and down and up and down. So, and the second component is the change of wind direction with time. So it's not just the speed changing, but it's also the direction changing. And this is what the control has to take care of. Okay. All right. So these are some rough values for roughness length. A roughness length is a value which indicates the roughness of the ground. And the higher the roughness of the ground, like the more stones, bushes, or buildings, or skyscrapers, whatever, the higher the roughness, the steeper the profile on the right. If you've got a very rough surface, you might even get a curve like this. So actually, the wind does not really increase with at all within the first 20, 30, 40 meters. And then you get a curve like this. So that will be the extreme. Yeah. With a high roughness length, you get a curve like this. With a low roughness length, you get a curve like this. Yeah. Okay. Well, yeah. Basics of wind turbine. Wind turbine has got a rotor, and a nacelle, gearbox sometimes, or a directly driven generator and a tower, switch box. Yeah, I think I do not need to get into this too much. Yeah, well. Yeah, there are two different concepts of running the generator. You usually want to have variable speed wind turbines to realize, on the one hand, as I already said, to realize the stall effect, but you also have to track the rotational speeds to match the maximum efficiency points for each wind speed. For example, if you have got a tip speed ratio of 6, yeah, the tip speed, like the wind turbine produces optimum, like power with optimum efficiency whenever the rotational speed of the turbine, like the tip speed, is 6 times as much as the wind speed. Now imagine a very variable wind, yeah, gusty wind, or high turbulence. You will lose efficiency if you get to a tip speed ratio of 4 or 7. Yeah, and therefore, it is important for the efficiency of the turbine to adjust the rotational speed of the turbine very quickly according to the wind speed. And this has to be covered by the control of the generator. And this is one concept which is realized in small wind turbines very often. You probably also heard from SMA that they have the Windy Boy. There are also other products on the market, for example, a good product from Siegfried Myers called Eocon, or a product from Power One called Aurora. You have got either a gearbox or you don't have any gearbox, depending on what type of turbine you've got. You've got a synchronous generator, and you've got a rectifier and an inverter. And in between here there must be some safety system to make sure that you get into stall mode early enough before the wind turbine destroys itself in strong winds. So this would be a very basic design. This would also, for example, be the design of the famous Enercon wind turbines, the large wind turbines from Enercon. Yeah, okay, so this is a very basic design with an induction generator, which is coupled to the grid directly. In the small wind sector, you sometimes can find this still. In the large wind sector, this is not used anymore. This means that the rotor has just got one rotational speed, which means that it almost never has got the optimum rotational speed to produce optimum power, like optimum efficiency, because it cannot adjust adjust the rotational speed to the wind speed. Therefore, these units usually also have quite late cut-in wind speeds, because like the rotational speed of the rotor and the gearbox and the induction generator, which is coupled to the grid frequency, is optimized for an average wind speed of, let's say, 4, 5, 6 meters per second, to have good efficiency during those wind speeds that occur quite often. And a more sophisticated approach, which is not used in small wind turbines, but which is used in large wind turbines very often, is an inverter system running here, putting a frequency on the rotor. Yeah, so the stator of the generator is connected to the grid. The rotor is rotating. And then if you put a frequency on the rotor, you can make the induction generator, which is coupled to the grid directly with the stator, into a rotational speed wind turbine. You simply add some frequency on there, which related to the grid frequency reduce the resulting frequency for the rotor. Yeah, and then here you can see some very important safety devices. As a wind turbine manufacturer, you have to take care of your wind turbine being N-1 safe, like fail-safe. If one failure occurs, this turbine still has to be safe. And therefore, you usually need two independent braking systems. So that is required by the major standards, this IEC 61400 standard series. The small wind turbines actually refer to the -2 series, like 61400-2. Large wind turbines are rather 61400-1. And but actually both standards require the turbines to be fail-safe, and they need two different braking systems. And in this case, this would be the brake disc, in front of the gearbox, mechanical brake, and the second one would be the generator brake, together with the stall effect of the rotor. Okay, let's go into the small wind turbines. And the small wind turbines, this is the 61400-2 standard I was talking about already. And in this standard, different wind classes are defined for wind turbines. Classes 1, 2, 3, and 4. And with these classes, there are referent wind speeds, VREF, in meters per second, defined in average wind speeds. And these classes are used for turbine design. And they are used to design generators, they are used to design mechanics of the wind turbine, they are used to design the whole structure of the wind turbine, also the safety system. The larger the class, like if you go from 1 to 4, the lower the requirements for the stability of the system. Like you see in the average wind speed in class 4, you have to sustain an average wind speed of 6 meters per second, whereas in class 1 you have to sustain an average wind speed of 10 meters per second. VREF, the reference wind speed, is used to calculate gusts. In this standard, this standard also describes how the design gusts have to be calculated. And then you compute a curve, a gust curve, starting from, let's say, 5 meters per second up to 60 meters per second, for example, as a 50-year maximum gust. And this gust and the resulting forces from this gust have to be taken into consideration in all your calculations for the generator, for the gearbox, for the shaft, for the for the basics, for the tower, for everything. Yeah, and you also you see here that the further you get to the wind class 1, the higher the demand, the higher the requirements. And well, at the end, if you set up a turbine, or if you design a turbine, you have to take care of choosing the right turbine according to the wind site. If you've got a class 3 wind site, and you set up a class 1 wind turbine, you probably paid too much. Because class 1 turbines are considerably more expensive than class 3 wind turbines. If you have got a class 1 wind site, then it would be near shore or offshore even, and you purchase a class 4 wind turbine, it will probably be destroyed after the first storm. Yeah? So take care of the wind site and the wind class of the site and select the turbine accordingly. Okay, so this was the first presentation. Shall we have another one? It's 5 to 12.